After watching the episode 1 and episode 2, I know you are comfortable with what is recursion, how to use it. Now we are ready to deep dive into several questions on recursion so that whenever we see a problem, we get the intuition, yes, we can solve this problem using recursion. Before that, there's a small topic, recursion tree. This is a very frequently asked question in interviews and it helps us a lot in imagining that how is recursion working. Okay. So we are going to learn recursion tree, but with the help of two example problems. Those two problems are very simple. I know you will be able to do it by yourself. It's going to be fun. Let me ask you the first question. Find the sum of n natural numbers. I know you can find the sum of n natural numbers very easily using a for loop or maybe the formula that you learn in high school. Sum of n natural numbers is n into n plus 1 divided by 2. But right now we are focusing on recursion. So I want you to solve this question using recursion. Alright, so as we broke down the problem of n factorial into a recursive problem, you can break down the problem of finding the summation of n natural numbers into a recursive problem as well. I want you to pause the video and try to code it by yourself. So we want to find the sum of n natural numbers, right? Sum of n natural numbers, which is equal to n plus sum of n minus 1 natural numbers. So again, we are going to write a function. That function is going to return us the sum of n natural numbers and we will trust that this function is going to work. Okay. And while writing that function, we will make use of that function itself. All right. Let us see with the help of code here. So we need to find the sum of n natural numbers. Let me quickly take input n, cin, and don't worry about the programming language. I will provide all the codes in the description. Python, Java and C++, all the codes will be there in the description. You can check that out. As of now, just focus on the concept. So I'm taking an input n and I want to see out or print the sum of n natural numbers, right? See out sum of n. I'm writing this function, the recursive function here, int sum. It will take the input n and then it's going to print the sum of n natural numbers. So again, I'm going to calculate a partial answer. Okay, partial answer. This partial answer will be the sum of n minus 1 natural numbers. So I will ask the function sum to return me the sum of n minus 1 natural numbers. And then what I'm going to do? I'm simply going to add n into it plus partial answer. This will be my entire answer. All right. But again, there's a catch. And now you know what the catch is. The base condition is missing. So let's say if we start from 5, we will be going to 4, then 3, then 2, then 1, then 0, then minus 1, minus 2. We should not go to minus 1, minus 2. And even 0. 0 is not a natural number, right? Natural number starts from 1. So we are going to stop at 1. If n is equal to 1, we know what we have to return, right? We have to return 1. Sum of n natural numbers where n is equal to 1 is 1. That's why we are returning 1 from here. We should not go below 1. So this is the base condition and this is the recursive step. The recursive step is we are writing a function to find the sum of n natural numbers. We know that this function is going to work. That's why we are making use of this function itself inside the function, right? So this is recursion. So it is very similar to the factorial example that we saw in the episode 1 and the episode 2, and most of the recursion questions are on similar lines. Sometimes instead of one there are two recursion calls that we will see very soon, and sometimes instead of one base condition there are several base conditions that also we will see very soon. All right, so now let us draw the recursion tree. What's the recursion tree? Recursion tree is nothing but what we have already seen in the last episode. So for example, let us call this function sum with a value of 5. It's going to make a call on sum with a value 4. It's going to make a call to sum with a value 3. This is going to make a call with sum with a value 2. It's going to make a call to sum with a value 1. And it's, yeah, and from here it will return. From here it will return because this is the base condition. It will return what value? It will return 1. Okay. Now 2 will be added to 1 and it will return 3. Now 3 will be added to 3. It will return 6. Now 6 will be added to this 4. It will return 10. Now 5 will be added to this 10 and it will return 15 to the main function. That's how this recursion is working, and this is the recursion tree. Every time when you solve the recursion problems, you do not have to draw this recursion tree, but this should be there inside your mind. And how would it help you? It would help you to analyze the time complexity and the space complexity, whatever the number of nodes are there in this tree. Okay, let me draw this tree nicely. 5, 4, 3, 2, 1. This is the tree. This tree is very much like a linked list, but it is a tree. Okay, it's a tree. And how many nodes are there in this tree? There are 5 nodes. Okay, and if we pass n to this, there are n number of nodes. That's why the time complexity is equal to big O of n. There are n number of nodes. By imagining the recursion tree, you don't have to draw the recursion tree every time. By imagining the recursion tree, you can analyze that what is going to be the time complexity. Time complexity is simply the number of nodes in the tree. Okay, you can also analyze the space complexity. Space complexity is equal to the height of this tree. The height of this tree. What's the height of the tree here? The height of the tree is big O of n. Again, the height of the tree is also big O of n. So this is the space complexity, this is the time complexity. Now, why is there a space complexity? We are not creating any extra vector, we are not creating any extra stack, queue, whatever. But as I told you in the last episode, if you haven't seen the last episode, make sure that you watch. There is an internal stack which is being maintained when these functions are called. Okay, and the function sum with the value 5 is going to call the function sum with the value 4, then function sum with the value 3 and 2 and 1. This will form a stack, and that stack is consuming memory. That's why it is big O of n. Alright, we will see another example that's going to make things very much clear. So let's quickly jump to the next example. I hope this is digestible. If you are not able to digest it, you can watch it again, okay? Or maybe pause the video, think about it. The number of nodes in the tree denotes the time complexity, whereas the height of the tree denotes the space complexity. Okay? So let's jump to the next example. So here we want to find the Fibonacci, the nth term of the Fibonacci series. Or you know what Fibonacci series is. Fibonacci series starts from, I guess, 1, then 1, then 2, first term, second term, third term, fourth term is 3, fifth term is the summation of these two, 5, then the summation of these two, 8, then the summation of these two, 13, and so on. This is the Fibonacci series. You must have learned about it. If you do not know, Fibonacci series is simply the starting 2 terms are given to us, and then rest of the terms can be calculated with the help of previous 2 terms. So this term is calculated with the help of these two, summation of these two. This term is calculated with the help of summation of these two. This term is calculated with the help of summation of these two. This term is calculated with the help of summation of these two, and so on. So that's how the Fibonacci series goes. And we need to find the nth term of the Fibonacci series. This is the first term, second term, third term, fourth term, fifth, sixth, and so on. We need to find the nth term. Alright, this is the question. Now think about it. How would you solve it? Every time when you solve the recursion problems, you have to think that what do you need to construct your answer? Okay, what do you need? Let's say somebody gives you an answer for a particular question. What would be that question? Alright, so here the question is, if I know the answer for n minus 1th term and I know the answer for the n minus 2th term, then I will be able to calculate my own answer. Okay, let's say if somebody is so kind that he gives me the answer for n minus 1th term and n minus 2th term, then it becomes so easy for me. It becomes so easy for me to calculate the answer for the nth term. What I need to find? I need to find the answer for the nth term. Okay, and if somebody gives me the answer for this and this, I will simply add them up and then return the answer, because the nth term of the Fibonacci series is the summation of n minus 1th term and n minus 2th term. Okay, that makes our life very simple. As recursion, we are very lazy. As recursive functions, we are very lazy. That's why we do not want to do the entire work. Okay, we want to handle this work to another recursive call and handle this work to another recursive call, and then we will add them up. Okay, this is the job that we are doing. We will add them up and then return. All right, so you can see there are 2 recursive calls here. Okay, we are breaking the problem into 2 small steps to find the answer for the n minus 1th term, to find the answer for the n minus 2th term, and then simply return the addition of both these. That's the Fibonacci series, right? So let's quickly jump to the code. I will explain you more with the help of the code, and then we will jump to the recursion tree. So here we need to find the nth term of the Fibonacci series. I'm taking n as the input. So this input is given. This is the nth term. And we need to see out, print Fibo. I'm naming the function as Fibo of nth term of the Fibonacci series. Now let us write the function. This function will give me integer answer Fibo of nth term. All right. Now partial answer 1 and partial answer 2. Two answers will be calculated here. So partial answer 1 is equal to Fibo of n minus 1. So I will request recursion to please give me the answer for n minus 1th term. Okay. I'm asking this function itself to give me the answer for n minus 1th term. And then again partial answer 2. Partial answer 2 is equal to Fibo of n minus, Fibo of n minus 2. Now we have the answer for n minus 1 and n minus 2. Both the terms are known to us, and we know that nth term is the summation of these two terms. So return partial answer 1 plus partial answer 2, and that's it. We are done. But again, these base conditions are missing. We need to find what the base conditions are. But I hope it makes sense to you, right? We are breaking down the problem into two smaller subproblems. Earlier, we were breaking down the problem into only one smaller subproblems. Sometimes we might have to break down the problem into n number of smaller subproblems, and we will see that gradually we will learn more about recursion. But as of now, we are starting with the very basics. So these are the two recursive calls. Okay, these are the two recursive calls to n minus 1 and n minus 2. And it is obvious, if we know the answer for n minus 1th term, if we know the answer for n minus 2th term, what is n minus 1th term and what is n minus 2th term, then we can simply add them up and return the answer. That's why we are making use of this function. Okay. And as we saw in the previous episodes, this function, we know that this function is going to give us correct answer. That's why we are making use of this function before even completing the function. Okay. That's how much we trust this function. We don't have trust issues with this. Now the base conditions. What do you think the base conditions should be? So let's say we want to find out the third term of the Fibonacci series. The third term will be the summation of first term and the summation of second term. Simple. Yeah. Let's say we want to find out the second term of this Fibonacci series. Second term, will it be a summation of first term and the zeroth term? There is no zeroth term, right? Let's say we want to find out the first term of the Fibonacci series. So first term would be a summation of zeroth term and minus 1th term? No. So starting two terms, the first and the second term, we need to know this. We need to know this, otherwise we will not be able to calculate it, because we should not go to the negative sides, right? So that's why if n is equal to 1, we should know the answer for this, and we already know the answer for this. It is given in the question, where f of 1 means Fibo of 1 is 1 and Fibo of 2 is also 1. It is given in the question. You can read the question properly. You will get all these links in the description, by the way. The question links will be there in the description. You can go and definitely try it out. So if n is equal to 1, what we need to return? 1. Okay. All right. If n is equal to 2, we should return 1 again. Okay. So these are the two terms of the Fibonacci series that we need to know. We will not be able to calculate them using this formula. All right. Nice. So this is the entire question. Let me try to run this and let me try to print this. I hope we get the correct answer in the single go. Yeah. Correct. Okay. Definitely give this question a try and try to imagine the recursion tree which is forming here. Try to imagine it. I will draw the recursion tree very soon, but just pause the video. Try to imagine how will it look. All right, so let us now draw the recursion tree. Let me take the example of 7. We want to find the 7th term of the Fibonacci series. Okay, 7th term. To find the 7th term, I am making two recursive calls. One to n minus 1, that is 6, and one recursion call to n minus 2, that is 5. So I'm asking recursion to please give me the answer for this and please give me the answer for this. I will simply add them up and I will find the answer for this. Now to calculate this, again two recursive calls are being made. One call to 5 and one call to 4. Okay, n minus 1 and minus 2. Again to calculate 5, two calls are being made. One call to 4, one call to 3. To calculate 4 again, two calls are being made. One call to 3 and one call to 2. To calculate 3 again, two calls are being made. One call to 2 and one call to 1. Okay, now these are the base conditions. This is the base condition, this is the base condition. We cannot go below this and we already know the answer for this. To calculate the first term and the second term, we don't have to do anything at all because these are the base conditions. We will simply return 1 from here. We will simply return 1 from here. That's it. Alright. But to calculate rest of the things, we again need to do the call. Okay. To calculate this 3, we need to make a call to 2 and 1 again. To calculate this 4, we need to make a call to 3 and 2. To calculate this 3 again to 2 and 1. To calculate this 5 again we need to make a call to 4 and 3. To calculate this 4 we need to make a call to 3 and 2. To calculate this 3 we need to make a call to 2 and 1, and that's it. Oh, okay, yeah, here's one more 3, so 2 and 1. So this will be the recursion tree. Okay, this is the recursion tree. I told you that sometimes the height of the recursion tree is not equal to the number of nodes in the recursion tree, and we can see here that number of nodes here are so much and height of the recursion tree is just equal to this. What's the height of the recursion tree? Just let me know in the comment section. Height of the recursion tree is simply this length. This particular length is the height of the recursion tree. So 1, 2, 3, 4, 5, 6. 6 is the height of the recursion tree, or we can say that height of the recursion tree is big O of n, where n is the number we are passing here. Okay, big O of n is the height of the. If we pass 100 here, the height will be 99. So we can say it is equal to big O of n only. Alright, big O of n is the height of the recursion tree. But how many nodes are there? Let us calculate the number of nodes. Okay, this will be a little bit of mathematics. I hope you remember these formulas. So in the first stage we have 1. In the first level we have only 1 node. In the second level we have 2 nodes. In the third level we have 4 nodes. In the fourth level we have 8 nodes, and so on till what? Till n number of levels, because we have n number of levels obviously, and is the height. N number of levels are there. So this is a GP. Is it a GP? Yeah, it is a GP, geometric progression, with a factor of 2, right? With a factor of 2. GP with a, what do we call it? Common factor? Common factor? No, not common factor. Multiplicative factor, whatever it is, we are just, every time we are just multiplying it by 2. This is a geometric progression and we need to find the sum of this GP. Sum of the GP is equal to r raised to the power of n minus 1 divided by r minus 1. So this multiplicative factor r is equal to 2 here. It is equal to 2. So it will be 2 raised to the power n minus 1 divided by 2 minus 1, which is equal to 2 minus 1 is 1. This will be 1, which is equal to 2 raised to the power n minus 1. Okay, for higher values of n we can simply ignore this one. For a very large value of n we can ignore this one here. So this will be equal to 2 raised to the power n. So these many nodes are there. These many nodes are there in the tree. So this is the time complexity of this algorithm. Okay, very bad. This complexity is very bad. We will see how we can improve this soon. When we will learn dynamic programming, we will see how we can improve this. Okay, I will give you the hint of it as well. So what we can say, number of nodes are 2 raised to the power n. So the time complexity is 2 raised to the big O of 2 raised to the power n. The space complexity is big O of n, where n is the height of the tree. This is the height of the tree, right? So that's how we can calculate the space complexity and the time complexity with the help of the recursion tree. We don't have to draw the recursion tree. We can just imagine it in our minds, because there are 2 recursive calls. The tree will go like this. Every node will have 2 children. Okay, the tree will go like this, and then we can calculate it in our mind. After a few videos, you will be able to do it by yourself. Okay, great. Now I just want to give you a slight hint of dynamic programming. We will start that after this course maybe, but what is being happening here? So we are calculating the answer for 5 here. Okay, we already calculated the answer for 5 by using these values, right? But again, we are calculating the answer for 5 by using all these same values. Why do we need it? Once you calculate the answer for 5, why don't you store it somewhere? And then when you need it here, why don't you take it from the place where you stored it earlier? Right? That is dynamic programming. That is a very simple concept. If you learn recursion nicely, you will be able to do all the questions of dynamic programming. That's for sure. Okay? Learn recursion. There are only 2 line changes which you need to do to make a problem from recursion to dynamic programming. Only 2 line changes. Okay? That's why pay attention to recursion. Okay. Alright, so I hope you enjoyed the video. You can rewatch it again if you're not able to understand everything, because there were a lot of things. We learned about the linear recursion, we learned about the recursion tree, we learned about the recursion where there are 2 base conditions, so you can rewatch it. Alright, let us meet in the episode 4.